Hello, my name is Craig Belgrad, and this is the quiz tutorial 1 for Physics 2 here at Georgia Tech. And quiz tutorials are essentially the same thing as test wrappers, but except this time the teachers have assigned us problems to do out of the textbook to go through and try to figure out solutions. So the professors gave us 3 problems, and the problem I chose was in chapter 18, it was problem 67. So the problem begins like this. So you have 2 wires that are near next to each other, 3 millimeters apart. So you have a current going in the left wire and the current going out the right wire. And you are 50 centimeters away from this point here, B. And that's the top view, and here it is from the side view. So part A wants you to calculate the maximum magnitude of the alternating magnetic field 50 centimeters away from the center of a long straight power cord that carries a current of 15 amperes. Both wires are at the same height as the observed location. So here's the formula for a magnetic field at a perpendicular distance r away from the center of the wire. So that point is just facing these 2 wires. So one wire would be blocking the other from this view. So that formula is B equals mu naught over 4 pi, which is 1 e to the minus 7th, times 2I over r, the distance r. So you're going to have 2 magnetic fields in this case. You're going to have B1, which corresponds to this inward going current, and that is mu naught over 4 pi times 2I1 over r plus d over 2. So that's half the distance from there. So that is the first one. The second one is essentially the same, except you have r minus d over 2. So this B2 would be closer than B1. So you want to find your B net, and since B2 is closer to B1, it's going to be B2 minus B1. So you have mu naught over 4 pi times 2I2 over r minus d over 2 minus mu naught over 4 pi times 2I1 r plus d over 2. So since I1 and I2 are the same in magnitude, they can both come out of the equation, and you can reduce it to mu naught over 4 pi times 2I multiplied by the quantity 1 over r minus d over 2 plus 1 over r plus d over 2. So you can reduce this even further to get d over r squared minus d over 2 squared. And since r is so much greater than d, you can cancel out this whole term, and it would just reduce to this whole term to simplify it, which would just be mu naught over 4 pi times 2id over r squared. So then your B net is just, you're going to take this whole formula, mu naught over 4 pi, which is, as stated before, 1 e to the minus 7, times 2 times 15 amps times 3 times 10 to the negative 3 meters, which is 3 millimeters, over 50 centimeters, which is 0.5 meters squared. And you're going to get the quantity 3.6 e to the minus 8 teslas. So this problem isn't necessarily bad. It just requires some algebraic manipulation, some simplification, but overall it's not a bad problem. So there's a part B of this problem. It says, explain briefly why twist a pair of wires into a braid when minimize the magnetic field at the location discussed in part A. So here you had these wires twisted as such. So as I flip this over, the explanation is alternating which current is closer to the point would allow every successive twist to cancel out the magnetic field produced by the previous twist, and so on. Therefore, this repetition would effectively minimize the magnetic field produced in the wire. So every single twist has one wire going before the next wire. So, the second wire might have the first current closer to it, but the previous wire might have the second current closer to it. So as that keeps alternating, each successive current or each successive magnetic field produced by the current is just going to cancel out the previous one. So that's how you minimize the electric field in that sense, because each successive one is closer and farther away. So that's how you minimize the electric field. And this last one, which is very similar to part A, theoretically, you could do part A just by plugging in the numbers as a whole without simplifying. You might get a more accurate number, but I just decided to simplify it for the sake of time and simplicity. But this is essentially the same as part A, but I'll do it anyway. So for 2 long parallel wires, like those shown in part A distance d apart and carrying conventional current I in opposite directions, find an algebraic formula for the magnetic field of a perpendicular distance r is greater than d to the right of the wires. So you're going to have the same B net, B2 minus B1, and you're going to do the same simplifying assumptions. So you're going to have mu 0 over 4 pi times 2I times the quantity 1 over r minus d over 2 minus 1 over r plus d over 2. So you're going to have the same things you did in the last problem. And since your r is going to be greater than your d, your this whole term down here is going to be just essentially r squared. So then your magnetic field is going to be, or your net magnetic field is mu naught over 4 pi times 2id over r squared. So it's very similar to the first problem, the same algebraic formula. Oops, apologies. Same algebraic formula. But I think in this case it's just more general, so you can just essentially plug and chug from there. So that is this video. I hope this helps you figure out this problem. It certainly helped me while doing it. So not too complicated of a problem, very simple. I believe this wire formula is on your formula sheet for the quizzes and tests that they give us. So ultimately, not a terrible problem, not too bad. So just apply the formulas, just recognize that the wires are carrying two different currents in opposite directions. You can find the net. It's just fairly conceptual. So hope this helps, and good luck on the final, guys. Hope we do well.